These are the brains of the operation. This is my advisor, Reka Thomas, and then her former student, João Gouveia, who's now at the University of Coimbra in Portugal. So first let's talk about what our problem is. So I let the kind of curly S sub plus to the R be the cone of R by R PSD matrices. And we saw in Tim's talk on Monday that given a polytope, we can always write it as a spectrahedron. To do that, we just take the inequalities that define the polytope and put them on the diagonal of a matrix and require that matrix to be PSD. So we can always write it as a spectrahedron, and a spectrahedron is an affine slice of the PSD cone. So in particular, we can always write it as the projection of a spectrahedron. But we can ask the question, given a polytope, what is the smallest PSD cone that will admit an affine slice, so a spectrahedron living in the cone, that projects to our polytope? So that's our question. Okay, and just for kind of a motivating example, it's been mentioned several times throughout this week. So for the stable set polytope on n vertices, we can define the theta body. And that's defined as all x such that we can find a u satisfying these conditions. The diagonal of u is x, and for every edge, the ijth entry is 0. So it's all x such that we can find a u making this matrix PSD. And that's a relaxation in general of the stable set polytope. And that's just because this outer product of the vector 1x with itself is PSD. And if we stick in a vector corresponding to the stable set of the graph, then that will satisfy these conditions on u. But it can also be seen that this containment is tight if and only if the graph is perfect. So in particular, if we have a perfect graph, then this defines an affine slice of the PSD cone of dimension n plus 1, and that slice projects onto the stable set polytope. So this is kind of an example where a polytope admits a very efficient representation by these PSD slices. Okay, so we define a PSD lift to be a slice of a PSD cone that projects to our polytope. This, for example, of what this looks like. If we consider the square in the plane, then we can slice the PSD cone with this affine space, and we project onto the xy coordinates, and that gives us our polytope. So here I have plotted the x, y, and z coordinates, and then we see that they project onto the square. Okay, so that's what PSD lift is. Now we define the PSD extension complexity to be kind of what we're interested in. It's the smallest r such that we can find a slice projecting to P. And we can think of this as kind of a measure on how well semi-definite programming can express our polytope. Okay, so we'd like to calculate this. And there is a way in theory to do this. So to explain that, I need a couple concepts. The first is the concept of a slack matrix of a polytope. So given a polytope with inequality description like so, and v vertices, the slack matrix is a matrix indexed on the rows by the vertices and in the columns by the inequalities, such that if we get the ijth entry by plugging in the ith vertex into the jth inequality and looking at the slack. So this is a non-negative matrix. Here's an example of what this looks like for this trapezoid. Here's the 4x4 matrix that I get. We see it's indexed on the rows by the vertices and in the columns by the inequalities. And if you plug in the vertices, you get the entries of the matrix. So one thing to know about these is these are not unique by any means. For example, we can scale the inequalities by positive scalars. That still gives a valid inequality representation. So correspondingly, we can scale the columns of the slack matrix by positive scalars and still remain a slack matrix. Okay, so that's slack matrix of a polytope. The other concept we need is called the PSD rank of a matrix. So this was presented earlier today in a slightly different context. So for us, the PSD rank is the smallest R such that we can find PSD matrices of size R by R, such that we can index the rows and columns by PSD matrices, and they'll inner product to give the entries of the matrix. So in particular, we don't require the matrix we're looking at to be symmetric, and we don't require the matrices on the rows and columns to be the same. So here's an example of what that looks like. So we have matrices on the rows and columns. Now, with these two tools, we can now say that the slack matrix of the extension complexity of the polytope is precisely the PSD rank of the slack matrix. So in theory, that gives me a way to calculate this PSD extension complexity, but in general, calculating the PSD rank of a matrix is something that's hard to do. There's no, at least not that I'm aware of, computational complexity results on it, but just in practice, it's something that's difficult. So a lot of times we can't apply this directly, but maybe we can find some bounds or use this to say something non-trivial about the PSD extension complexity. And often we call this, from now on, I kind of call this PSD extension complexity as the PSD rank of the polytope because of this theorem. So all of this is kind of a generalization of some work that Yannakakis did. So if I replace the PSD cone with the non-negative orthant in the definition of PSD extension complexity and PSD rank, I get the definitions of linear extension complexity and non-negative rank. And Yannakakis showed that this linear extension complexity is equal to the non-negative rank of the slack matrix. Just to give a little intuition about what these are, the linear extension complexity, that measures how well we can represent our polytope as the projection of a higher dimensional polyhedron, where how good a lift is how many facets the higher dimensional polyhedron has. And non-negative rank, we can think of it as kind of the same picture as the PSD rank, only we require non-negative vectors on the rows and columns. So in this context, quite a few results have been shown. There have been shown optimal kind of efficient lifts for the permutahedron and regular ingons. It's been shown that there don't exist small lifts for cup polytopes or traveling salesman polytopes. And it's also been shown that calculating the non-negative rank of a matrix is NP hard. Okay, so for the rest of the talk, I'm just going to kind of give an overview on some of the things that we know about the PSD rank of a polytope. So for a general non-negative matrix, we have this lower bound, which is essentially the square root of the usual rank of the matrix. It looks kind of complicated, but all of this amounts to is if we have a PSD factorization, we have these matrices and the rows and columns. So if I write those matrices as vectors, that gives me an upper bound on the rank. Okay, and this is tight for general non-negative matrices. But for slack matrices, we can do better. So for the slack matrix of an n-dimensional polytope, the PSD rank is just bounded below by the usual rank, which is n+1. And additionally, you can show that just looking at the support of our matrix, this is the best lower bound that you can hope for. So kind of support-based lower bounds have proven pretty effective in the non-negative rank case, but this is the best you can do in the PSD rank case. So in particular, if we think back to the example of the square, this theorem says that the PSD rank of the square is at least 3, so this lift was optimal in that sense. And this raises kind of a natural question: which polytopes have this, which polytopes achieve this lower bound? We call these PSD minimal polytopes. Okay, so in order to answer that question, I need one more rank. So if we have a non-negative matrix and I look at an entry-wise square root of that matrix, there's many possible such square roots because we have a sign choice for each non-zero entry. And so the square root rank, what I do is I take the ranks of all those possible square roots, and then I take the minimum of those numbers. And just for an example, for this matrix, the usual rank is 3, but square root rank is 2, because if we put a -1 in the top row, the rank becomes 2, and it's easy to see that the rank can't drop lower than that. So how do we connect this to PSD rank? What we do is, if we have a rank 1 PSD matrix, we can write this as UU transpose for some vector. So then if we have the inner product between two rank 1 PSD matrices, and we write out what that means, we see that it's just amounts to the vector inner product of U and V squared. And so once we notice this trick, it's pretty immediate that square root rank is exactly equivalent to the PSD rank when we only use rank 1 matrices as our factors. So square root rank is an upper bound. And our characterization for these PSD minimal polytopes is a polytope is PSD minimal if and only if the square root rank is equal to n+1. So this isn't a great characterization because we still have to deal with all these possible square roots, but it is easier to work with than just calculating the PSD rank of a matrix. And we've been able to use it to characterize all PSD minimal polytopes in R2 and R3. So in R2, the PSD minimal polytopes are just the triangles and quadrilaterals and nothing else. So just a combinatorial characterization. In R3, there's 4 combinatorial classes that are always PSD minimal. Those are tetrahedra, triangular bipyramids, quadrilateral pyramids, and triangular prisms. That's just because all those classes have a very low number of either vertices or facets, less than or equal to 5. But the interesting case is for octahedra. So given an octahedron, there's kind of 3 groups of 4 vertices that are kind of special. I can view the octahedron as a bipyramid over these 4 vertices. Or equivalently, I could view it as a bipyramid over these 4 vertices or these 4 vertices. And in a regular octahedron, all of these groups of vertices will be coplanar. And of course, for a random octahedron, none of them will be coplanar. So what we say a biplanar octahedron is when at least 2 out of these 3 groups of vertices are coplanar. And it ends up being, those are precisely the PSD minimal octahedra. And the only remaining class is biplanar cuboids, which are the polars of the biplanar octahedron. Okay, so this example shows that PSD rank is not constant over combinatorial type. Now there is an object from polytope theory called the oriented matroid, which encodes the coplanarities of all the vertices. And so an oriented matroid can differentiate between a biplanar octahedron and a non-biplanar octahedron. But we have other examples that show the PSD rank is not constant over the oriented matroid. So it could still be useful for a classification, but it's not a silver bullet, I guess. So open questions. Can we come up with a geometric classification? Something that doesn't rely on all these entry-wise square roots. And kind of weirdly, thus far, the all-positive square root has been sufficient when checking this theorem. If you're PSD minimal, then the all-positive square root achieves the lower bound. And if you're not PSD minimal, well, of course, the all-positive square root doesn't achieve the lower bound. So is this true in general? That would be a much nicer characterization, but we haven't been able to show it yet. Okay, so the lower bound that we showed before doesn't grow with or it only grows with dimension. It doesn't grow if we're in a fixed dimension and our polytopes are getting more complicated with more vertices and more facets. And then in the non-negative rank case, there's kind of a nice simple lower bound that says the non-negative rank is bounded below by the log of the number of facets. So we'd like something kind of corresponding to this that grows with the number of vertices or the number of facets. We haven't been able to do it in the general case, but we can do it for generic polytopes. So a generic polytope is one whose entries of the vertices form an algebraically independent set. So if we have a generic polytope in Rn with v vertices, the PSD rank is bounded below by nv to the 1/4. So this lets us say that a generic 129 gon has PSD rank 5. Here's a 129 gon. And this is the simplest concrete example of a polygon with PSD rank 5 that is known. So there should be a lot of room for improvement here, but thus far we haven't been able to find anything. We'd like to show a 7 or 8 gon with PSD rank 5. And I'd also mention that there are a few other lower bounds that have come up recently. I guess it's more existence of polytopes with high PSD rank. And those were done by Briette, Dedouche, and Pokuda in a paper. And what they say is that there exists 0, 1 polytopes with exponential PSD rank. So there do exist polytopes with exponential PSD rank. We just can't find really explicit examples. Okay, so shifting gears to upper bounds in the plane. No upper bounds was known until recently, so in theory it wasn't known if I could have a 10 gon with PSD rank 10. A few months ago, Yaroslav Shitov showed that the non-negative rank of a V-gon is bounded above by 6V over 7, so that gives an upper bound on the PSD rank. We were able to improve this slightly. We can show that all pentagons and hexagons have PSD rank 4. And by showing that every hexagon can be obtained by projecting a biplanar octahedron, you can show, or that's how you show that every hexagon has PSD rank 4. Then for larger V-gons, we just split them up into the convex hull of many hexagons and pentagons. And that lets us show that the PSD rank is bounded above by 4V over 6. Okay, so one more major open question in this area. So it's known that this matrix, where we have the ijth entry is I minus j quantity squared, that matrix has non-negative rank essentially log n as n grows. But just using our square root rank upper bound, that matrix has PSD rank 2. So for general matrices, we can get an arbitrarily large gap between PSD rank and non-negative rank. What's not known and what would be interesting is to know whether we can find a family of slack matrices where we can find a large gap. So if we had such a family, those polytopes would be much better expressed by semi-definite programming than linear programming. And that's all I had for today, so thanks for listening.
this result of Dadouche, which you said that among 0, 1 polytopes, there are, most of them have exponential PSD rank, right?
Yeah.
Exponential PSD extension.
Yeah.
How many are these in comparison? Because there is a result of Rothfuss.
Yeah. What they do is
same topic for non-negative, for normal extension complexity.
Yeah, they took Rothfuss as a result and generalized it to the PSD rank case. It ended up being a lot more technical. But you want kind of a ratio of.
I mean, are these numbers of the same order or different?
I don't know off the top of my head. I would think the ones with high PSD rank extension complexity would be, there'd be many more of those because of the, I mean, there's doubly exponential many 0, 1 polytopes, and they were getting I think it would be much higher for the PSD rank with high PSD rank, but I'm not sure off the top.